My name's Amy Mashad, and I'll be announcing the speakers this afternoon. We will do all three presentations, and then we'll have a question and answer period afterwards. So just hold your questions, write them down, and keep those in mind so we can ask some good questions at the end. They did ask me to remind presenters to make sure you sign in on the sign-in sheet this afternoon if you haven't done that today. And we'll be breaking, let me see, at about 4:15 directly out back here. So anyway, I'd like to announce our first speaker. It's Jeffrey Dake from the U.S. Army Crime Lab in Georgia. And he'll be presenting on, oh, I know it's a long name, so I'm going to have to read it. He's going to do method validation for the analysis of condom and sexual lubricants using direct analysis mass spectrometry.
Good afternoon. I want to apologize. The name sounded great until I tried to fit it onto a PowerPoint slide. So it's a little longer than I should have made it. And despite the sophomoric implications, unfortunately, my presentation this afternoon is going to be fairly dry. But with all of the discussion about method validation and instrument reproducibility, I think you'll find the presentation itself to be quite enjoyable. This is our official disclaimer. The Army and the Department of Defense disavows any knowledge of my statements. It is not to be construed as official military policy or a recommendation by the military for any product or chemical listed herein. So what was the purpose of this validation? Essentially, we were looking for a technique that would involve rapid and easy discrimination of two common condom lubricants, polydimethylsiloxane, or PDMS, which is commonly employed as a lubricant, and it's present on a majority of condoms produced, at least in the United States, to my knowledge. And inoxanol 9, which is very specific for condoms and sexual lubricants because it's often used as a spermicide. So the instrumentation that we validated for this method was direct analysis mass spectrometry with time-of-flight mass spec. You can see the instrument here, particularly in the picture on your right. That's the actual sample inlet port. It's open to atmosphere. It allows us to hold samples directly within the source and perform real-time analysis of samples. It can preclude steps like extraction, screening, cutting by directly sampling and getting mass spectral information from your samples. It involves disposable media, which of course is great for quality control. And it gives us rapid analysis over a large mass range, typically somewhere between 100 and 1,200 or 1,500 AMU. So the compounds of interest that we were analyzing, to get accurate mass information from this instrument, we used an internal tuning compound. In this instance, we used polyethylene glycol with an average mass of 600 AMU. What this does is it gives us repeatable peaks over the entire mass range so we can tune the instrument. Our instrumental tolerance is plus or minus 5 millimass units. Because the instrument doesn't involve a separation technique like GC or LC, to increase specificity, we are using accurate mass as opposed to nominal mass. We also use an internal QA/QC. Once we've tuned the instrument, we want to make sure that our tune is accurate. So we used Reserpine, which is a turkey tranquilizer, and it's got a mass of 609.281 in the protonated molecular ion. So you can see on the bottom is polydimethylsiloxane. It's got a repeating polymer unit of OSI-CH3CH3. And it has a mass range of about 200 to 600 on the DART. The nonoxynol polymer, because it actually is produced as a polymer with the 9-chain unit being nonoxynol 9, the spermicide, has a repeating O-CH2-CH2 group. And it covers a range of about 350 to 900 AMU. So there is overlap between the two. So already we can see that there may be a possibility that discrimination in combination may not be possible. Specifically, I want you to note that nonoxynol 9, the actual spermicide compound of interest, has a mass of 617,426 in its protonated molecular molecule. So a little background. Currently in the laboratory, we are screening both of these materials as they are polymers by FTIR. This is a IR spectra of polydimethylsiloxane. We've got 5 characteristic peaks, all below about 1280 wave numbers. And polydimethylsiloxane is great for IR. It's a strong IR absorber, and it gives us a really good signal even in small sample amounts. What you'll see is the nonoxynol 9 has a very distinguishable spectrum from PDMS. However, it absorbs in a similar region, and it doesn't have a very strong absorption in IR. So when you talk about a condom or a sexual lubricant that is predominantly lubricant, or PDMS, and maybe 5 to 15% spermicide, you use this factor that the PDMS is a strong absorber and nonoxynol 9 is a weak absorber, and the fact that there's much more PDMS than nonoxynol 9, it sometimes becomes difficult to detect nonoxynol 9 in the presence of PDMS. So in our laboratory, what we'll end up doing is further extraction and separation using C18 tubes, and then reconstitution in methylene chloride, which nobody really wants to work with. So it becomes kind of a long process to analyze and detect nonoxynol. Additionally, because it is polymeric, we have difficulty determining that it's specifically nonoxynol 9 present, as opposed to some other nonoxynol compound. So when I told my boss that I was going to be validating the DART, he kind of got the impression that it was going to look something like this, kicking back at my desk, throwing darts. But we designed a process that would optimize our instrumental parameters for both our tuning compound and our compounds of interest over the entire mass range. Then we wanted to establish our methodology or our protocol for analysis, establish limits of detections for our analytes of interest, compare to actual case samples to get an idea of what type of background or competition we might see, and then ultimately implement it in an analysis scheme. And I guess the last step would be come here and talk about it. So in the instrument, we used 3 parameters. There are many parameters you can vary, but the 3 parameters that has the most effect on your sample analysis are the orifice voltage, which is that inlet which you can change the voltage. A lower voltage will give you less fragmentation. The system will perform similar to a CI mass spectrometer. As you increase the voltage and it gets stronger and stronger, you're going to see more EI spectra, a lot of fragmentation. And again, since we're not doing any separation, more fragmentation becomes a lot more difficult to interpret. Orifice temperature is the most widely variable parameter. You can go from somewhere around 100 degrees C all the way up to 500 degrees C, so there's quite a range. And changing that temperature is going to affect the types of molecules that you volatilize and ultimately sample. And your detector voltage, just like any other instrument, as you increase the voltage on the detector, you're going to get an increased signal with increased electronic noise. Conversely, as you decrease that voltage, you're going to get a weaker signal but much less noisy spectrum. So we wanted to evaluate that to determine, again, if this lack of separation, we want to decrease our noise to the point to make our spectra much more interpretable. In all, we ended up with 36 different parameter sets that we created a matrix out of, and we ended up testing all of these samples. So to give you an idea, thankfully these colors showed up. To give you a good idea what our data is looking like, you can see in blue is our PDMS peaks, and in orange are our nonoxynol peaks. While they do overlap, you can see that there is definite clear separation between the two. With PDMS, what we actually end up seeing is 2 different polymeric chains based on where the PDMS molecule fragments. The 355 and 371 fragments are actually complementary fragments, and the 429, 445, et cetera, through different masses in the range. With nonoxynol, even in a purchase standard of supposedly nonoxynol 9, we get several other polymers present. We're able to see all the way down to nonoxynol 5 up to nonoxynol 15, but of course, there's our compound of interest, that nonoxynol 9 at 617. So yes, there's overlap, but step 1, we were able to clearly distinguish them at the same time. So in our parameter set, essentially what you're looking at on the y-axis is the number of peaks we saw for our chemical compound. So since we want to maximize our signal over our entire sample range or mass range, the more peaks, the better, the more pieces of information we can obtain. Across the bottom is each discrete temperature that we did. And then we did 4 replicants of our PEG internal tuning compound. So what we were looking for was a high bar and equivalent bars for each color. For 15 volts, we had a problem with one of our sample sets. Again, I said that 5 millimass unit range was kind of our limit, and one of our peaks fell out. So clearly those parameters weren't the best. But as we look at 325 degrees, you can see that not only do we get a high number of peaks at 15 peaks for PEG, but we're seeing reproducibility. We're getting the same result every time we put the sample in. At 35 volts, our reproducibility wasn't as great, but 275 looked to be our best. So we wanted to take these forward, analyze our analytes of interest, and see which one was more effective for those. Now, I have no charts for PDMS because PDMS is pretty much insensitive to all of the parameters we used. You could set it to almost anything, and the system was going to find PDMS. With nonoxynol 9, again, the same thing. We're looking for a large number of peaks, so that would be our y-axis, and then our x-axis is our varying temperatures. And you can see again that 325, we saw a great number of peaks with nonoxynol 9, which covered a wide range. At 275, it wasn't quite as responsive. We needed a little bit higher temperature to get that nonoxynol 9 moving, which ultimately led us to decide on 15 volts and 325 degrees for our parameters. So moving on to limited detection, essentially what we did was we started with serial dilutions from 100 nanograms per microliter all the way down to 1 nanogram per microliter of each analyte. We tested each dilution in triplicate to demonstrate reproducibility, again using that 5 millimass unit tolerance. We had 4 different examiners perform it to evaluate inter-examiner variability. As you can see in this picture, essentially the sampling technique's as simple as holding something in front of the source. You know, obviously the concern with that is, well, if you hold it to the left and I hold it to the right, is one of us missing the spot? So we wanted to get this data to see if we could find inter-examiner variability. We tested all these solutions on FTIR so we'd be able to compare both of our instruments and get a clear idea of how these 2 instruments perform for these types of samples. And we tried just dipping the rods in solution. As you can see in the background, there's that glass jar with the rod just hanging out. We also used a 1 microliter syringe to deposit 1 microliter of our solvents to, again, increase our reproducibility and our specificity. This is our typical data for PDMS. On the top is our 100 nanograms per microliter solution. The bottom is 5 nanograms. And you can see peaks for PDMS in each of them. It's clear that there are several more peaks for PDMS in the more concentrated sample. And when you look at the abundances, the overall abundance, or the maximum abundance on our top spectrum is about 20,000 counts. And the bottom we're down to 2. So it's something that you would expect. It's about 10 times, a little less than 10 times as concentrated. So this is what we're looking for. And ultimately we found PDMS pretty efficient on FTIR and on DART. The order of magnitude was essentially the same. It was a little more sensitive by DART than FTIR in these pure samples. But Nanoxanol 9 had a strong preference for DART. We were an order of magnitude more sensitive, which again leads us to a much stronger screening tool. And it's very interesting because it complements the IR. As I said earlier, the IR is not very preferential, or the Nanoxanol 9 is not a strong absorber for FTIR, but it seems to love the DART. So for what our Casework shadowing did was essentially we took 86 case samples. They involved actual case samples with all of the case-related information stripped out. We also used lubricant standards, lotions, cosmetics, skincare products. We also had some people simulate case samples, and that means exactly what you think it means. So those daring souls went out and got us realistic samples so we could evaluate how these instruments would perform, particularly when we introduce things like body oils, detergents, and other types of things that will commonly be in the environment that a case examiner is going to have to deal with. The work was performed by 2 different examiners, myself and another examiner at the laboratory. It was performed completely blind. One examiner would test a sample on FTIR, transfer that sample into a glass vial with a sample identifier. No information was provided as to what the sample had in it or what the results were. And then the second examiner would test it by DART. To eliminate any kind of bias, we flipped it halfway through, and the person who was doing DART now had to go do IR and vice versa. So this is what our typical sample came out to be. We're looking for the PDMS in this spectrum. This was a cutting from a pair of underwear, and we found body oils by GCMS. We found several compounds that we see in lotions and cosmetic products. So we knew that this was a pretty dirty sample. But when we look at the results, you know, we clearly can pull out these PDMS peaks. And it's not just 1 peak or 2 peaks. We're getting several peaks associated with PDMS with this high mass accuracy. So what this is telling us is that even though we're dealing with complex mixtures in the absence of a separation technique, we're still being very effective at identifying our compound of interest. Our competition or competitive ionization from other molecules isn't hindering our ability to detect this compound, even in realistic case samples. And our ultimate results. We had an 80% agreement with PDMS. And what I mean by that is that approximately 25% of our samples were positive both by FTIR and by DART for PDMS. So the IR saw it, the DART saw it. About 50% of our samples were negative on both instruments. The IR didn't see it, the DART didn't see it. When our disagreement came about, we were actually fairly shocked. We were expecting it to be one way or the other. Either the IR is going to be a much better technique, and thus we can use the IR to screen for DART, or the DART's going to be a much more effective technique, and we can use the DART to screen for IR. But it turned out we had discrepancies going both ways. We had 10 samples that were positive on DART, which means the DART was able to identify compounds associated with PDMS, and the IR came back negative. Conversely, we had 7 samples that were positive by FTIR and no result by DART. And we thought hard about these types of samples. We compared our data, and what we were finding was we had a lot of indications of weak samples. So the most likely resolution for this is that these samples that we were having contradiction were near the limit of detection of both instrument. So as you reach the limit of detection, any minute error, such as holding that sample in front of the source, any slight error is going to increase the possibility that you're going to miss your analyte. So it could be that we're dealing with low limit of detection issues, and that would be why we're having disparities in both directions. It's also possible that we could be dealing with a sample that has IR competitive absorption with PDMS, and it was difficult to identify PDMS in the sample because of, say, a body oil or a lotion product, but the DART had no problem differentiating those two. And conversely, you could have competitive ionization in the DART, allowing you or disallowing the ability to see PDMS, but they have two different IR absorptions, and it's easy to distinguish by FTIR. The double bonus is the noxinol 9 had 100% agreement. In all of the samples that we found in noxinol 9, it was present by DART, it was present by FTIR. And the majority of samples were negative for noxinol 9, but we had strong agreement in the negatives as well. So what we ultimately determined from this portion of our validation is that the Accutop DART was effective for the screening of the noxinol 9. It eliminates all of the extraneous extractions that we were doing before. It saves us money by not having to buy costly C18 tubes. It prevents me from having to smell like methylene chloride when I get home. And ultimately, it is improving our efficiency and our accuracy within the laboratory. As I said, with FTIR, we're only able to identify a polymer associated with noxinols. But this exact mass information allows us to identify noxinol 9 being present. We did have inconsistencies with PDMS. As I said, it could be possible interference from other compounds, issues with the limit of detection, and what we're doing next in our next phases is attempting to address these issues. So we want to improve our detection abilities with PDMS. We could do things such as increasing the volume. What we found was that if we deposited 1 microliter of sample into the DART, it gave us, say, a response of 10,000. And if we added 2 microliters, we would get a response of 20,000, and then 3 microliters and 30,000. So it wasn't exactly linear, but it was close to linear. So we could always increase our sampling amount, move ourselves above that limit of detection, and evaluate whether or not it is limit of detection issue that's giving us discrepancies. We're also considering using internal standards to perform semi-quantitative analysis of PDMS. PDMS is used in lotions, cosmetics, skincare products, sexual lubricants, and condoms. But they're used in different concentrations in all these different types of products. One of the things that we're interested in evaluating is using, say, a known concentration internal standard to develop information as to whether the PDMS that we're seeing in a sample is highly concentrated and then thus more likely to have come from a concentrated source of PDMS, such as a condom or a sexual lubricant, or in low concentrations and then likely to be present from, say, a lotion or a cosmetic product. Another examiner has also proceeded in validating the analysis of lotions and cosmetic products themselves by DART, and currently has characterized 40 different compounds commonly used by the lotion and cosmetic industry. This is giving us advantageous results. We're able to see compounds that we've never seen by GCMS because of issues with volatility in the separation. The absence of a separation technique in this instance has really benefited our laboratory. We're able to see compounds that we were never able to detect before, giving us much more information as we look at lotions. And again, it's a very rapid technique, so it allows us to rapidly screen these things and pull out all of this information. So I'd just like to say thanks to the NIJ for giving me the opportunity to speak here, and Amy for being our moderator. And I'd also like to specifically thank Derek Dorian, one of the other examiners at the laboratory, who was instrumental in performing this validation. And he helped me put together a lot of slides for this presentation. So if any of the slides were not to your liking, those are the ones he made. And according to Amy, we'll be waiting on questions. So that will be it.